All right, so welcome to the second lecture. After introducing the physics of NV centers and the basic sensing protocols, during the second hour, I will focus more on applications, especially in the second half of it. And I have one topic still to discuss in terms of methodology of nuclear magnetic resonance, especially if you use a single NV center as a sensor. There are some differences between conventional NMR and NV-based NMR. You have atomic sensor. It measures the magnetic fields of external spins, and these spins, if they're in liquid, they also can go into sensing volume and leave the sensing volume. The volume is very small, and the number of spins is also very small. This very small number of spins provides you some unique advantages, but also some disadvantages. So first, on the plus side, what is positive about this? You don't need any magnetic field to create a signal. Usually NMR is about large magnets. So you need to create some polarization. For very small number of spins, there is a statistical polarization. There is always overshoot of spin up over spin down. For one single spin, it will be 100%. One single nuclear spin will be either spin up or spin down. Even if it's not polarized over time, it averages out. But in every single moment, there will be spin up or spin down, so it's 100% polarized. For 10 spins, there will be square root of n overshoot. So for 10 nuclear spins, there will be 3 usually dominating over other. So it will be as 1 over square root of n. N is the number of spins. So if you have 1,000 spins, square root of n is 30, you have 3% polarization. And this is typical situations. Very large signal. Remember, classical NMR worked with polarization of 10 to the minus 5 in a very large magnet. But in this very small number of spins, you get a few percent just for free, even a zero magnetic field. So it creates very strong signal. So the signal can be easily detected by NV because it's sensitive magnetometer. But if the molecules are going in and out, their spins are not kind of correlated. That's why the signal is fluctuating. So now, instead of a very weak but persistent signal in a conventional NMR, where the polarization exponentially dependent on the magnetic field, then in this nanoscale NMR, you have a polarization which is very high, but it's always fluctuating with its phase and amplitude. So the signal is high, but its fluctuations are leading to broadening of lines. That's why you don't usually get very, very highly resolved line. Here is a picture how we see these external spins. Every spin is a magnet. There is always overshoot of spin up or spin down. That's why you get results in magnetic field. But if these magnets are diffusing, there is a redistribution of magnetic moment, and the amplitude and phase are fluctuating, and you get a diffusion broadening. And that was the example that we have seen before already. And we centered 2 nanometers from the surface. The line width is about 100 or 200 kilohertz, and that's because of this diffusion. So this is a problem if you want to resolve spectra with a J-coupling resolution, about 10 hertz or 100 hertz. So here you're very sensitive, but your signal is fluctuating and get diffused. And it's very general problem how to reach a high spectral resolution if your signal now is having a short coherence time. So if you have 2 frequencies in your signal, and they overlap, they start to beat, and if you can detect the very first beat in a frequency domain, you get 2 components, and then you can resolve the spectrum. But if the coherence time of the signal is shorter than the frequency separation, then you cannot resolve 2 frequency component, and they are now merging with 1 maxima, and you can show in theory that the information content of this spectrum in terms of ability to resolve components is going very quickly to 0. So this is a challenge, and in general, it's a significant challenge in metrology. So if you don't see this first bit, you are hardly capable to resolve components. The feature information, the information content is going very quickly to zero. There is, however, now an opportunity where the quantum system can do better than a classical sensor. Before, I was discussing this in terms of sensing this signal with a classical sensor, like an oscilloscope, and trying to get this bit. But a quantum system can do better than this. And this is collaboration with my colleague, Alex Rezka from Hebrew University in Jerusalem. And I show you how the QND, the single shot measurements, can allow you to resolve spectral components better than given by this ability to see the first bit in a signal. So I remind you again, the measurement protocol within vCenter. When we detect magnetic fields, we take in vCenter from MS equals 0 state, we go to coherent superposition and acquire the phase. This is a top view on XY plane. And then this phase is measured again in along z direction after flipping the spin by a second, by half pulse. Usually for a single in vCenter, if you are somewhere in a block sphere here in the XY plane, you will get a set of 0 and 1 if your measurements is projective. So even if you're in a superposition state, every single measurement will give you 0 or 1, right? But the statistic will give you information about the real state. So if you are in superposition state, you will have 0, 1, 0, 1, but then the weight of them in a total measurement statistic will give you the information about the state. So there is a projection noise here. That's why your measurements are always noisy, and the precision limits that we have discussed before. This delta B is given by this projection noise. So this projection noise is giving the sensitivity of a magnetometer. There is, however, no noise for two states along on the poles of the block sphere 0 and 1. If you are in 1, so you can measure many times, so you don't have any projection noise. For a quantum system, measure it in eigenstate, there is no projection noise, and so it's basically you get a noiseless train of results. Okay, so this is just from the back action of measurement device on the quantum system. Now, if you have two frequency components acting on an vCenter, you can make control fields in a way that if you have just one frequency component, the block vector returns back to the eigenstate, and you have no excitation in the system and no noise. Let's say 0 photons or 0 change of state. But if you have two frequency components, now you are not ending your block vector in the on the pole of the block sphere, and then you have photons emitted or like some projection noise appearing, and that's the sign that you have two frequencies. So basically, by measuring spins in a regime where you do QED measurements, you can now discriminate between state where you have two frequencies or one frequency present in the spectrum by appearance of the noise. But if you have only one frequency present, there is no noise at all. And it has some consequences on the resolving power, because you are sitting on a point where there is no noise. And so here it's a bit different view on this. So it's a probability of spin flip of an vCenter, and it's shown as a function of the separation between some control pulses present in an vCenter control, and there is some stroboscopic points where the evolution of the quantum system returns back for the single frequency present in the spectrum or separation of components to be 0. It's the same as a single frequency. And at this point, so you have no noise in the system, so it returns back. But if you have two frequency components, you get the spin flips, and this can be detected with a very high precision because you are on a noiseless plateau. So of your in vCenter is always given a 0, 0, 0, 0, or 1, 1, 1, 1 if there is only one frequency present in the spectrum. So I just illustrate this. Yeah, please.
Sorry, I have a question from the previous line. So omega, what is omega s exactly physically? It's like
omega s is a kind of a rotating frame in it.
Okay. So these are the all omega 1 and omega 2 are the beating
the two frequency components.
Okay, and omega c.
So it's a carrier of dynamical decoupling. It's a bit sort of, I apologize for not kind of coming here deeply. So we would like to change the rotating frame. That's why we do have some radio frequency pulses having this omega c. And so this is a carrier, and then we detect the tuning from the carrier. Yeah, it's a transition to rotating frame.
Frame of reference, basically. The difference between the two Hamiltonians is the frame of reference, basically. Okay.
So I want information also for the frequencies, and the probability actually depends on the detuning. So the probability also grows with the detuning. So from this, I also will get the information about the splitting between frequencies. So it's, of course, what I discussed mostly, that I can distinguish either is one or two, but also the probability rate will depend on the splitting between these components. I also will get spacing in frequency space. Now, I can also illustrate this in a very simple picture. Exactly, yeah. This.
Yes, how much can you detune? What's the restriction for the detuning the frequency?
Dynamic range of this. So it's a driving frequency of the microwave. So we can detune this typically by maybe 20 megahertz or so from the carrier, and have dynamic range of about up to 20 megahertz. It's about yeah. I'll show you an experiment in a second. But before I give you another overview how block vector evolves. So if you do this evolution where it always comes back if you have just one frequency, and it can be different phases. So you oscillate the function of action of the external field, but you always get back to X, and then the last pass bring you to Z, and Z is noiseless, remember. So this is for a single frequency, and for two frequencies, you get a little bit of off here, and also for the other phase of acting radio frequency, it's not returning to X, and it will not return to Z, and you will get some photons, some flips of the spin that you can detect. And so you are in a very low background where there's no noise, and this flip can be detected with very high accuracy. So here's a example of realization. Remember, so we typically, in a very simple experiment, don't do this very high quality projective measurement, but using NV-center nuclear spin, we can do this. We can measure a nuclear spin in this single short manner. I show you again a time trace. We can put a threshold here. Our distribution and photo counts now can be separated into spin up and spin down and spin up. And here, so we can measure the 0 and 1 with very high precision. The inaccuracy here is about 0.03%, and this is room temperature single NV-center. And so now this protocol can be applied. So we apply spectrum with different frequency components, and we now watch in the probability of spin to be NV-center to be flipped. So for a single frequency, there is no flip, and we plot this transition probability. And for two frequency component now separated for different splitting. So the signal frequency, so splitting is 0 kilohertz, is blues, blue histogram, 1 kilohertz, 2.5 kilohertz, 5 kilohertz, lead to different results. So the transition probability is 0 for single frequency, right? So you measure many times, but there is no flips as expected, because NV-center always come back to the same state. But if you have big chromatic spectrum acting on it, you start to depart from the zero transition probability, and you get more and more events of the spin flip. And so here you detect several frequency components by acquiring the flip of the in V center, now measure it here in a single shot. Now the measurement time here, or the coherence kind of time of the signal, is the same, was here about 20 microseconds, so 50 kilohertz in the frequency space. And we can detect the presence of different frequency component already for a frequency separation of 1 kilohertz. So now remember, we have discussed this in the metrology perspective, with two frequencies. So we say that if you have 1 bit to be detected, you get separation, and now you can detect two frequencies. And if you have no bit detected, there is no separated peaks, and you cannot resolve the spectrum. But here we had a splitting, which was 50 times less than coherence time of the signal. So more or less this picture. We can still detect the presence of two frequency components. Okay, so it shows that you can reconstruct the spectrum, and having a single NV center give you additional advantage, ability to detect these quantum jumps and detect spins with high precision, give you a new opportunity. It's of course a very model experiment. It's not real application yet. It's a synthetic signal applied to NV center. And it's only example for two frequencies present. And there is ongoing work, especially in the series side from Alex Sredska, whether you can generalize it to multiple frequency component, and whether you can reconstruct the arbitrary spectrum from this type of measurements. So it's a bit of open question how much you can learn about this very dense spectrum with very short coherence time of the signal, to which extent you can fully reconstruct the spectrum. All right, maybe one last point about enhancement of NV centers. We have discussed a lot about improving T2 time, and we also know that using nuclear spin you can do a single shot readout of electron spin with auxiliary qubit. There is also effort to improve NV center fluorescence detection itself. And all the other experiments and methods will benefit from this. Typically, if you work with a flat diamond, you get most of your photons remaining inside of diamond because of total internal reflection. So having solid immersion lenses allowing light to escape better, diamond is a very important element in many experiments. Sometimes not really compatible to sensing of external spins, for example, because NV center need to be very close to the surface, and only for large seals then it's possible to place something on a flat side. But it's this engineering of diamond allow you to improve the photon collection efficiency by about factor of 10 compared to a flat diamond surface. For low temperature, there is also effort to couple color centers to photonic crystal structures, photonic crystal cavities. There is also a possibility to get color centers inside of pillars. It's also enhance the outcoupling of light. Oops. So for photonic crystal cavities, you can get enhancement on both sides. You can get a faster decay of color centers, but also a better directionality of emission. And here you see the example of silicon vacancy center emission. In case of free space, having like a couple of nanosecond fluorescence lifetime, but being in a cavity and tune it in a cavity, it can have a higher rate of fluorescence emission, but also and higher directionality emitting in one particular mode. That's allow you to improve collection efficiency. So there is another path to improve collection efficiency and improve detection efficiency of spins, is to use photoelectric signal instead of photons. Here is a structure of NV center, energy levels, but now shown inside of a band gap of diamonds. So you have a valence band, you have a conduction band, and now your ground state and excited state are within a band gap. So typically you excite your NV center from a ground state to excited state and it decays. But if you excite with high intensity laser, there is non-zero probability to take the electron from the excited state and put it in a conduction band. Now your diamond become conductive. You have an electron in a conduction band, and diamond is a good conductor. It's insulator only because there is no charge carriers in a conduction band, but mobility is very high. Now your diamond become conductive for some time before you suck this electron to the electrodes, if you have electrodes nearby. And NV center can recapture the hole from the electron from the valence band, leaving the hole, and get back to the NV minus state. So you start with NV minus, you put your NV center to NV zero, producing one electron. You take the electron from the valence band, leaving a hole, and you return to NV minus. After this cycle, you generated one photoelectron and one hole. And if you have a voltage across the area with your NV center, you can detect these electrons and holes, measuring the spike in photoconductivity. So that's additional channel to detect color centers. And because your photoionization happens via excited state, it carries all the information that excited state population carry too. It has all this spin contrast, very similar to the one coming in photoluminescence. Here I show you example of optical and photoelectrical image of color centers. The optical one, that's very traditional confocal scanning. So you scan a laser beam and you measure photoluminescence. Here I show the intensity in counts per second. Here's a color. You see single NV center. Sometimes we have here two. And on the bottom, you have one of the electrodes. That's why this area is a bit shadowed. The second one is here on the top. And if you measure the photocurrent across these electrodes on the bottom or on the top, you get the same spots here. So you can recognize exactly the same dots here. Every single NV center has it imprint also in photoelectrical image, where we measure photocurrent instead of photons. The photocurrent is shown here in femtoamperes. You can ask whether it's a high photocurrent or low, so from a single color center, and how we compare this. So 100 or a few hundred femtoamperes is, of course, a lot of photons, photoelectrons per second. Is much more than photons. Actually, you can drive it all the way up to 10 picoamperes, and that would correspond to about 10 to the 9 photoelectrons per second detected from a single NV center. That should need to be compared to a few 100,000 photons per second detected in a photoluminescence. So you can also do the ODMR, magnetic resonance, now plotting the photocurrent as a function of the applied microwave, and you get this deep exactly as an ODMR. And nowadays we also can do this experiments with very shallow implanted NV centers, similar to that we use it for NMR, even located just a few nanometers from the surface. Yes.
But there are subtle differences in the pictures, no? I mean, did you do a quantitative analysis of the two? I mean, I think most are there, but some are not there. And also there's one under the electrode and things like that.
So close to the electrodes. Of course, there is a background here. There is some photoresist left or so producing a high fluorescence background. That's, of course, we don't see in the photocurrent. There is some differences here too on this side. I think that there is some shadowing from the second electrode, and because photoelectric signal is kind of 2-photon signal, so it suffers faster with lower in intensity. So it might be that this part, which is a little bit shadowed here, is suffering more in intensity of the photoelectric signal compared to optical. Then It also can be that, I mean, I think majority of spots are visible in both cases, but some of the centers visible in photoelectric signal might be not visible on optical if it's not in V center. So you can also see some color centers in photoelectric readout which are not visible optically and even not in V centers. But in this case, majority of correspondence is there. It's good. Yes, it's
How intense does your light need to be to excite it into the induction band?
high intensity. You need to saturate this transition to get high population of the excited state, and typically it's about 1 to 2 milliwatt going to the objective, to the microscope objective. So compared to 100 microwatts for optical. Oh, yeah, you made a start.
Detected via ODMR and electrically detected magnetic resonance, or is it expected that it's exactly the same?
Expected to be in the best case exactly the same, because the photocurrent basically represents the population of the excited state, and the fluorescence emission also represents the population of the excited state. So it's expected to be exactly the same.
Okay, thank you.
Is the spin contrast because of the different lifetime of the excited state, or what's the reason that you have different photoionization rate from MS0?
Okay, yeah, that's a good point. Yeah, it's exactly the same reason that for fluorescence. So from -1 is +1 state, the system goes shelved very quickly to a singlet and fall down very quickly to 1E state. And from here, the energy of photon is not enough to ionize. So the green photon can take your electron from the excited triplet to the conduction, but not from 1E. So, and that's mean that this state protects you against producing photocurrent in the same, this is also dark state in the ODMR. So it's 1-to-1 sort of correspondence. So we can do all these measurements that we did before with the photoluminescence also in photocurrent. There's, however, some differences. So the photocurrent need to be detected using very sensitive amplifiers. And optical detection usually is very robust because you use single photon detectors, APDs, that have high temporal resolution, but high gain amplifiers for electrical signals usually are very slow. So there are some differences how to handle the pulse measurement, but nevertheless, by doing it right, you can also detect Rabi oscillations. This is on the left side. You have optical, let's say, also Ramsey sequence. I think, yeah, you get optical signal on Ramsey. On the right side, you get photoelectric signal. You can put your sensing points in a maximum of gradient of the fringe, and now measure the change of your Ramsey fringes picture, and that's give you access to a magnetometry. We can do it for optical and photoelectric measurements with a single NV located very close to the surface, and we can also estimate the sensitivity by sitting in the maximum sensitivity point and then measuring the phase of the second pi half pulse. That give us this sensitivity measure in sensitivity as a function of measurement time. So we get a slope. So the longer you measure, you get better sensitivity as usual, but the slope give you a sensitivity per square root of hertz. It's about 4 microtesla per square root of hertz for a single implanted NV center close to the surface and detected electrically. So now we have discussed already before, we discussed that for a very good NV center, a single NV center with millisecond coherence time, you can get a sensitivity of about 10 to 20 nanotesla per square root of hertz. And here we have about 4 microtesla. So it's about close to 100 times less sensitivity, although we discussed that we detect much more photoelectrons. So there is a contradiction. So why it is so? So you can also see in the signals, although the femtoamps, like 10 femtoamps is more than 50 counts per, I think it's 50 kilocounts per second should be, but it's still larger, but the noise is higher. And that's because the amplifiers are noisy and we are kind of far away from the optimum amplification here. So if you would, there is an ongoing effort in the field now to make our amplifiers to be better, to be limited only by kind of electron shot noise. So fundamental limits in electrical measurements, but currently it is much more technical noise from imperfection in detection system, and majority of this noise can be cancelled, we believe. And according to estimation, the sensitivity of electrical readout, at least in a simple model, should be much better than sensitivity of so electrical readout should be better than optical one, but the current measurements are suffering a lot from the noisy amplifiers. All right. So I was a bit slow in the beginning, so I'm now coming to application in biosensing. So was initially planned for a second hour, but we will go relatively quickly. So I would like to discuss some applications beyond just measuring nuclear magnetic resonance, and NV-Center provides the ability to measure fields at room temperature, ambient condition, non-vacuum, and it's of course very interesting tools also beyond NMR. For example, you can think about measuring currents through membrane channels. If the current going through is a 10 picoampere, and if your magnetic field sensors is very close, they can measure the field you expect is within measurement range of NV-Center. It's about fraction of a nanotesla. Biomolecules undergoing chemical reaction usually are using catalytic centers and enzymes, and those are unpaired electron spins producing a 10 nanometer standoff distance, the field of about a microtesla. There is also effort to detect action of neurons using NV-Center magnetometers. In a very initial optimistic estimate by Lloyd-Hollenberg group, they expected to have a B field. When neuron fires, there is an action potential and current associated with this, and it's 100 nanometers distance. They have estimated the field of about 100 nanotesla. More recent estimation, but also measurements show that the B fields are much smaller, on the order of hundreds of picotesla, but still within a range where NV-centers can provide enough sensitivity to capture the dynamics. Those are, of course, very important processes, and even if I get capture of some of them and some details of them, it will be very important for the field of life sciences and medicine. And it's not about replacing other techniques addressing this, but providing a new tool. Even a small improvement here can provide enormous impact in the field. So it's not like in quantum computer where you need a factor, 1,000 to be better than normal computer. Here, 10% improvement in temporal resolution, spatial resolution, and sensitivity can be very essential. This is also another distinction of sensing as a field. So how we can interface this NV-centers with biological systems? So there can be two sensing modalities, and one is to have this shallow NV-center as a layer implanted, and then you grow the cells on top of it, or you use diamond nanoparticles doped with NV-centers, and these diamond nanoparticles can get transported inside of cells. Then you can measure even inside of the cell. Yes, this.
So just I have a question to the previous slide. So you showed the possibility of measuring magnetic fields. So I mean, with NV centers, you can also measure electrical fields. But why did you decide to go for magnetic fields by, for example, the neurons?
Indeed. So actually, for neurons, there is also a proposal to measure electric field. But electric field, actually, the best point to measure electric field is across the membrane. So then you would need to insert your sensor across the membrane. But electric fields outside decays very quickly because they get shielded by water. And so if you're outside, if you, like a few nanometers standoff distance, it's better to measure magnetic fields. They are not damped. But if you are across the membrane, there is also proposal to sense the neuron field with electric field component. And so there are two modalities how to handle this. So either to interface diamond with cells by growing cells on top, or take nanodiamonds and then insert them or transport them inside of living cells. So I say here now a few words about nanodiamonds, because this is now the way how to go inside of cells, inside of living cells, and they can be produced by essentially two techniques, either using the high pressure and high temperature growth of diamond, or by a CVD growth of diamond from plasma. In both cases, you can get some material that is doped by nitrogen, having this yellow color as a sign. If you irradiate micro and nano powder with electrons, you get greenish color. This change comes from the presence of vacancies. Vacancies absorb the light in red region of the spectrum and leaving green as a hole in absorption, and that creates this greenish color. And so if you anneal this nitrogen and vacancy containing nanodiamonds or microdiamonds, you get the powder with pink color, similar to that you have seen in the very beginning, nanodiamonds doped with NV centers. Often the challenge of handling diamond particles is aggregation. When they come from reactors, they have a lot of sp2 groups, and they're hydrophobic and they tend to aggregate. So basically removing these unwanted sp2 groups and making them hydrophobic is important field of research. Sometimes when try to stabilize them by folding polymers that are charged around them, and then because of electrostatic repulsion, they get stabilized in the solution. And this is important for any of this transport application, because you need to put them on the cells. The cells take these nanodiamonds by endocytosis. It's very important to have them not aggregated. And it's also important to have them not aggregating to be able to be released from the cell and not being cytotoxic for many applications related really to tissues studies. There is a strong effort in making them targeting certain biological molecules, and this is essentially about creating the surface groups, amino, hydroxy. There's also effort in making the functional shell out of proteins that have some targeting groups in the end, so like antibody targeting reactions, or even hybrid particles having a silica coating. The advantage of silica is that for silica there is a very rich already set of functionalization existing from the chemistry. All this is available in terms of functionalization of diamond particles. So yes, this.
Diamond is also already.
How large you mean the particle? So it will be large diamond now, affecting your protein, sort of. Yeah, that's the question.
How will you couple the?
How you couple it to the protein? Yeah. So the idea would be to have some complementarity. So you have an antibody kind of group sitting on the surface of diamond, and that will sit on a particular protein. So that's sort of the ideal case. Yeah.
Or for spin-spin coupling, if you have a spin.
It would be not spin-spin. It will be really electrostatic attraction of complementary proteins. Sort of the targeting will be not by spin-spin forces, but by electrostatic forces that are responsible also for functioning of the proteins. So this targeting attaching can be either by complementarity of DNA and RNA or complementarity of a peptide. Okay. And here's an example how you can see now these nanodiamonds inside of cells. It's a joint work with Jiaming Kai group in Wuhan, and here you see a living cell. It's fluorescence microscope, and we opened the detection channel for emission of NV centers and nanodiamonds. Nanodiamonds were kind of spread on the culture of cells for about 10 minutes and then washed away. And after this, some of them penetrated inside of cell, and you can see these individual dots. This is single NV centers inside of very small nanodiamonds. You can now, if you have antenna on top, a microwave antenna, you can do exactly the same experiment like you did before, but inside of the cell. You can do also applying pulses, like dynamical decoupling. Also continuous dynamical decoupling is possible. You see in both cases, you can extend your T2 time a few tens of microseconds. And we also have compared with Jiaming the performance. Remember, I mentioned before that this continuous dynamical decoupling can be very interesting because it's very robust. You don't need pulses, but it's also energy robust in terms of if you don't want to heat your cell very much with high microwave power, so you need to limit the power of your microwave source. And then the question, how much of decoupling, how much of T2 time you can reach for the same Rabi frequency. Here inside of cells, we have compared this for continuous dynamical decoupling versus XY. And so you see that for low Rabi frequency, continuous dynamical decoupling outperform the pulsed one. So you can do better job for this biosensing measurements with continuous dynamical decoupling compared to the pulsed one. Those are examples. So some examples what you can do now inside of nanodiamonds. Unfortunately, not so much complicated or complex experiments have been done, but these nanodiamonds sensors inside of cells are already very widely used in very straightforward measurements. One of them is measurements of radical concentrations. It's based on relaxometry. When you have radicals and fluctuating magnetic fields, they have components at lambda frequency of NV, and that leads to kind of flipping of NV center electron spin and shortening of T1 time. And you can, with this, study chemical reactions. For example, redox reaction of ascorbic acid. During this redox reaction, there is a radical forming, and so having this reaction outside of diamond lead to significant change of the T1 time. So here we see the distribution of T1 time with radicals present outside. It's mostly about 30 microseconds. And this is nanodiamonds without this radical environment, without chemical reaction going on. And so it's a very significant decrease of T1 time. With this, you can detect the presence of the radicals. I need to say that also T1 time of nanodiamonds is often shorter than this a few milliseconds of T1 time in bulk diamonds because of this complex surface effects and radicals always present, even without the radicals you want to sense. There is some radical concentration on the surface. That's why this distribution of T1 time is shifted to shorter times compared to bulk diamond value, but there is a clear contrast in this distribution. And I think that the NMR inside of cells will come. It just requires ability to perform more complex pulse sequence, but also better nanodiamonds, better T2 time smaller size, and I think then like NMR experiments also will be possible. But sensing with NV centers is actually not limited to sensing of B field. We have already discussed that NV center states can be affected by the electric field. Electric field actually change the zero field splitting. So the D parameters can be changed if you apply the field along NVX, and minus and plus one state can be splitted if you apply the electric field perpendicular to NV center X. In addition, the D parameter, the zero field splitting, is a temperature dependent value. So if you change the temperature, the D changes, and this separation between 0 and plus and minus 1 state changes. It can be seen like in the simplest picture, like the effect of extension of diamond lattice, because the D parameter comes from a dipole-dipole interaction between electrons forming NV centers. The closer these electrons are spaced, the higher is dipole-dipole interaction, the larger is the D, and the more extended its wave function of NV center electrons, the weaker is dipole-dipole coupling, and the smaller is the D parameter. So this is the reason why the D changes. And it's very fundamental, right? So it's not dependent on other parameters, it's only expansion of diamond. It's also decoupled from the B field. The B field change the separation between plus and minus 1 level, but doesn't change the D. So you can now do very precise temperature measurements. If you measure the D parameter, the splitting between 0 and middle of plus and minus 1, and this is example of these measurements with NV center in nanodiamonds. Two spectra recorded at 310 and 296 Kelvin. And you can maybe don't see the difference very clearly, but there is a difference, there is a shift. And you can track the shift. The shift is 70 kilohertz per Kelvin. And of course, the narrower are your lines, the better you can track the shift. But so you can clearly measure it with a few degree precision. Here I show you the result of measurements of a single nanodiamonds sensor. So this spectrum measure it for several different temperatures, and you can track the center between these two lines and reconstruct it as a temperature measurement. Yes.
So like you mentioned that the temperature shift is around 70 kilohertz per Kelvin. Like, is it always linear for low temperature as well?
Yeah, around room temperature, and it's because expansion of diamond lattice stops at cryogenic temperature. It is not sensitive to temperature at like 10 Kelvin or lower. It's not following this route. But this is very linear in a physiological temperature range, sort of. Yeah. No.
Is there some temperature dependence on T1 as well? The
temperature dependence on T1, and T1 goes all the way to let's say maybe about a few tenths of nanosecond at 600 to 700 Kelvin, leading to loss of DMR effect and optical pumping. But I don't think so that would be competing with this in terms of sensitivity for this very small range, but for very high temperatures, so that can be also a contrast. Yeah. All right. So now, why these temperature measurements are important? Well, temperature is of crucial importance in life sciences. Many biological processes are governed, their rate is governed by temperature, and there is a need to actually make a thermometer inside of cell. So we know that microscopic thermometers are very well developed, but make a thermometer inside of cell with submicron resolution, this is still a challenge. The golden standard at the moment to make a thermometer inside of cell is to use fluorescent dyes, which fluorescence intensity depend on temperature. So here you have a picture of fluorescence dye, which is inside of the cell. Cell is compartments are marked with this dye, and you see the difference in intensity. Actually, the dye fluorescence changes and fluorescence lifetime changes. Here it's a film image. Fluorescence lifetime is marked, and you see this difference in color, and fluorescence lifetime can be recalculated in terms of a temperature change. And so that is a golden standard for high resolution, high spatial resolution thermometry inside of cell. This technique has reported enormous gradient of temperature sometimes, up to a few Kelvin existing inside of cells, and this also provoked a discussion in the community. This is one of the discussion papers saying that measured results of very high gradient inside of cells are not compatible with the thermodynamic model of the cell. If you take all the ATPs that cell produces, and this is known quantity, and take heat conductivity inside of cells into account, then you don't expect a gradient larger than a millikelvin. And the 10-degree gradient was measured, and so there is a 4 orders of magnitude difference, which is a puzzle. So this puzzle is not having an explanation at the moment. The question is whether the model is too simple, and is the thermal conductivity of the cell is not like just the water, which well can be. All the measurements with the dye was not accurate enough, and dye was reacting on some other parameters, like for example pH or radicals. This all can affect the lifetime of the dye. So that's why we and other groups are trying to apply this diamond thermometry, which is less affected by external parameters, to the temperature measurements. So we collaborate with several groups doing the functionalization of diamonds, including Anke Krüger now at Stuttgart University. She's trying to basically create nanodiamonds having no artifacts in this temperature measurements, and she is doing by putting a peptide on the surface of diamond. This peptide is stabilizing the electric field, because electric field is actually a competing factor with temperature. So having an electric field change on diamond surface can create an impression that you have a temperature change. And I'll show you how that happens, in fact. So you here we have our diamond in water and then coated with BSA protein, and you see that the spectrum changes dramatically for this non-treated nanodiamonds, because BSA protein carry charges, and this is BSA protein, which is also present inside of cell. Just by docking to NV center or docking to nanodiamonds can significantly change the spectrum. That will be for you like a illusionary temperature change. So that's what it would be a measurement sort of of the temperature change, although it's just the BSA docking. And using these functionalized nanodiamonds, we get spectra which is much less sensitive to external kind of proteins present in the solution. Diamonds are more stabilized and delivering much better reproducibility of the spectral shape. And so we don't have any more like measured fluctuations of temperature which are not coming from temperature. The error bars here in the temperature measurements now with this functionalized nanodiamonds are much smaller. And so this basically control of surface in chemistry is extremely important in this field. Actually making nanodiamonds, functionalizing nanodiamonds and controlling their surface is a very key element, which cannot be overestimated as an important parameter. So we can also now...
Sorry, I have a question about the functionality of the cells after injection of the diamonds. Do you see that it's changed, or it will be the same, or it will not affect any?
Don't inject nanodiamonds, but we rather incubate them with a solution, and cells are taken them by endocytosis. And so by this itself, we don't think that this process leads to a temperature, especially if very small nanodiamonds number is transported, so just a few per cell. your question is about toxicity or anything?
Yeah, that the cell change its functionality after.
Usually we carry it with very small number, and cells are also taking other particles usually. So they of course, it's not only in diamonds that they like to take, they take any particles, but we usually work with very, very low number. It's about just 1 or 2 per cell, and those are just a few nanometers. But that it can be, so we didn't study this in detail, but a very small number. Yes. Here you have example of a cell having actually 3 nanodiamonds now, not 1, and we can, with our confocal microscope, we can track them inside. So here it's not just sitting for hours in one diamond because it's moving now. So you need to track where it's moving. So we always do 8 points around and see in which direction it's moving. And we travel with our laser focus along with nanodiamonds, and we can track the trajectory inside of cell. And during this time, we can measure for many tens of minutes without losing it, the spectrum. And remember that the position of these lines of ODMR is carrying information about the temperature. The measurement of these lines is simple in this experiment, but it's not very sensitive because we have a broadening of the line in this experiment, and the sensitivity of tracking it depending on the line width, like in magnetometry. So we also work on developing techniques which makes this temperature sensing more precise. For example, we apply microwave pulses now to make a Ramsey fringes-like measurements. This is difficult to do in rotating nanodiamonds by applying just short pulses. We need to take into account the diamonds can rotate with time, so we need to make it very robust, and adiabatic rapid passage is one of the methods where you sweep the frequency through the resonance, and then it can be very insensitive to fluctuations and in a dipole orientation. So with this, you can do Ramsey fringes now for moving and rotating nanodiamonds, and the decay of this fringe give you a line width is now much narrower than you've seen before. So it's a few microsecond time, coherence time, and that give you much better tracking accuracy in frequency space. Yes. Well,
back to the temperature sensing, I just wanted to ask, is there any effect of like local heating when we are optically trying to measure the...
There is effect indeed. So it's also a very important kind of artifact. So we have calibrated this. We need to stay to avoid heating above 0.1 degree, at least for the cells that we were working. We need to stay with our laser power like below at 10 microwatt. Yeah, that's
considered as an offset in all of your temperature measurement, or can it vary during the measurement?
Not very good to have this offset because also absorption of laser can change with time, and you might interpret this as a heating because of biochemical reaction, but it's not. It's better to avoid this completely, and so it's actually having a invisible range laser below like 10 microwatt give us at least this artifact below 0.1 Kelvin. Yeah,
that will limit the sensitivity. Thanks.
So we have now ability to apply pulses. We can also do more in this. So basically constructing the pulse sequence that is not sensitive to a magnetic field. So we excite coherences that are only sensitive to D parameter and not to splitting between minus and plus one. We call it thermal echo. It's just a sequence of pi half and pi pulses, and this basically get imprinted phase that is measured in the end, which is only dependent on a D, but not on a fluctuating magnetic field. That make a line width much more narrower because there is radicals on the surface of diamond. They create fluctuation of magnetic field, but this echo cancels this and only get sensitive to D. And so this is now Ramsey fringes measured using this echo, and they now decay with a 30 microsecond coherence time. So it's about 30 kilohertz line width. And remember, the shift is 70 kilohertz per degree. So now you get per degree a shift of 2 line widths. So now you can track much better. So potentially already with a millikelvin temperature. This I need to say, it's I'm happy to say that this results also were supported additionally by better nanodiamonds. made by collaboration with Gavin Morley from Warwick, and they were also enriched even by carbon-12. So it's also better nanodiamonds, but also better protocols given the line width of the temperature-sensitive transition to be on the order of 30 kilohertz. And so now we can, with this technology, we can apply it to cells and try to reproduce experiments where the mitochondria have been perturbed by the special agent that affect the proton transfer through the membrane, FCCP, and so we have doped our cells with the nanodiamonds. We have chosen nanodiamonds that are close to mitochondria. We have conducted some control measurements, so having just continuous measurement of temperature gives the same results. There's no fluctuations coming from just observation, and then we dropped the temperature of the stage by 4 degrees, and our measurements results shown the same. So this is just a control. And then we basically try to reproduce the result of activation of temperature gradient by this FCCP. So we have measured evolution of temperature, and we couldn't see any difference. We were even not sure that our measurements are right, so we were waiting before, after some time, and then after again dropped by on demand our stage temperature, detected the drop. So in these measurements we couldn't reproduce the results that have been before reported using fluorescence emission-based technique. So different technique, but so we don't see here the consistency of the results here in this particular cell, of course, and this particular kind of FCCP activation. So we couldn't see the effect of FCCP that was reported before using nanodiamond thermometer. So our results were showing very constant temperature, no 10-degree change of temperature in this case. Right? Yes.
So my question is, how can you really decide or distinguish if the nanodiamond is inside of the cell? Because, I mean, do you also observe the velocity? So does it change inside the cell? Or, I mean...
And first of all, we wash them away, but we also do a Z-scan. And so we, as standard in fluorescence microscopy, we can see that so the cell is not zero thickness in a confocal. We can see them inside between two membranes.
Question here on the thermometry. The NV fluorescence is also somehow reacting to pH, right? With some charge state change?
The charge stability of NV can be affected by pH, yeah.
But here you would just get some change in contrast then or something
If
like this.
NV is an NV0 state, this is effect. So it doesn't contribute to a ODMR signal at all. We just will reduce the contrast of this, but it's it won't affect this spectra at all. It will be just lower contrast.
That's because you said it. How strong does it react to pH?
I think that's really depend from one nanodiamond to another, size dependent. Yeah, but it's maybe some percentage going to zero. Yeah, so some percent.
I think pH is also very similar to pressure. So hydrostatic pressure in a liquid. So I'm trying to measure that.
How pH is similar to pressure. So what is?
Just like, I think it's just like if you have high pressure, then there are more particles close by.
Sense of effect on NV0, NV minus, you mean? Or
yeah.
Because I think for the temperature temperature sensing inside the cells, for example, the next slide, you are using the FCCP to treat the cells. But actually, I think there's a temperature gradient in the cells. So, which means that the position of the diamonds are very important. FCCP works for the mitochondria, but if the nanodiamonds are not at the mitochondrial site. I think this gradient probably is not.
Yeah, exactly. So we were not especially targeting mitochondria, but we were selecting diamonds that get stuck close to mitochondria. So we can see mitochondria in a fluorescence image too. And somehow a lot of them actually get stuck near mitochondria, at least the nanodiamonds that we have. And so we were measuring near mitochondria, at least within a kind of confocal, 200 nanometers.
Okay, yeah, thank you.
That's exactly the question also, how much gradient you have in cells. So
because I'm also curious about
models say that you don't have a gradient, and so it's an open question.
Okay.
About activation of gradient or observation of gradient. You can also do more in terms of temperature measurements. So often therapeutic effect on cell is related to temperature rise. For example, in phototoxic drugs, the release of the drug, which is often carried by a particle, is triggered by a temperature change, and we have been able now to combine the functionality of NV Center with a drug delivery device and the sensor of the temperature, and this is collaboration with Tanya Weil Group here at Mainz at the Institute of Polymer Science. So here you see the nanodiamonds again transported in cells, and when irradiated with infrared light, we have been able to hit the nanodiamonds by absorption of light by coating of nanodiamonds, and then this rise of temperature was measured and correlated with phototoxic action of the drug. So you can see inside of cell that your drug is starting to work, to get released, and that can be done with simultaneous measurements of the temperature. You can also do more than this. You can correlate measurements of temperature with measurements of radical concentration, which often also trigger the chemical reaction. This is also collaboration with Tanya Weil, where we have observed that the heating, localized heating that measured by the NV Center lead to polarization of macrophages, that they start to convert to another state, which is characterized by the production of the radicals, and this production of radicals can be now measured by NV Center relaxometry. So there are a few parameters that can be measured in cell. One is now temperature, that was method that we have discussed before, and the other is concentration of the free radicals, and you see that they both are correlated. So the rise of the temperature by a few degrees lead to now like change of the state of the macrophages. So this is now some change in temperature, which we induce it by laser radiation. We call it single cell fever, that we can kind of now activate on demand the biochemical processes inside of cells. So all these experiments have been done on NV centers. So we were staying with NV centers for the whole lecture today, but maybe in the last part, I would like to very quickly discuss other color centers present at diamond. I think that was already touched by Nir. So there are also other dopants that do have some advantages in terms of sensing, but also in terms of application in quantum communication. One of them is a silicon vacancy color center. Instead of nitrogen, you get silicon dopant in diamond. And silicon atom is a bit larger than nitrogen, so it doesn't fit very well to carbon position and like to occupy a place between two vacancies. So it's a silicon vacancies, but silicon is large that it's basically get shifted to a position between two vacancies. And it's highly symmetric structure, leading to the fact that the fluorescence emission spectrum of this color center is very, very narrow. So it's just a few nanometer line width. And actually, Elke Neuer was first report in single silicon vacancy centers that are bright enough to be detected at a single site level in nanodiamonds. At this time, it was not very well understood whether you can detect single silicon vacancy center or not. More recently, the centers have been explored as element of quantum networks, but also as temperature sensors. For silicon vacancy, unfortunately, spin states are not readable at ambient condition, only below 4 Kelvin. But optical emission, narrow optical emission, get a shift with temperature, and the origin of this is very similar to that of shift of ODMR of the NV center. Also here, in the simplest model, the wave function of electron get more expanded, and that lead to the shift of the optical transition now, and this shift is about a wave number per degree Celsius. So you can see the difference in optical emission recorded for 15 and 30 degrees. So it's not very large shift, but can be detected. But for measuring this, you don't need any microwave, so it's very simple. You can just track the fluorescence spectrum, and with this you can also reconstruct the temperature. You can also estimate temperature sensitivity by measuring accuracy and temperature sensing versus time. You see, here you get a precision of about a degree per second measurement time. With in these centers and ODMR, we had a shift in the very last advanced measurements about line width per degree. So here you have a shift of one wave number on about 300 wave number width line, so about 0.3% per degree. So the method itself is less sensitive, but it's very simple. We can track this fluorescence emission without applying any microwave, and this simplicity also provide important application area. I can also dope this silicon vacancy and other color centers inside of nanodiamonds. It's collaboration with Tanja Weil group. It's actually work done in Mainz here at the Max Planck Institute for Polymer Research. Tanja Weil team doped or grew nanodiamonds from nanographenes, sp2-like structures, by adding in a high pressure, high temperature growth chamber silicon and germanium. And it turns out that the presence of the seed molecule significantly facilitate formation of nanodiamonds. So if you take a graphite as a source, under certain condition, you don't form diamond, you end up in a graphite, but under the same condition, same pressure, this nanographene molecule act as a seed and can now transform to a sp3 diamond with silicon and germanium incorporated. And so here you see the picture of this nanodiamonds grown in Mainz here with size of they can do from a few nanometers to a few tens of nanometers, and doped with silicon vacancy center with this line at 737 nanometer. At low temperature, it splits into spin selective transitions. This is this fine structure here. And germanium vacancy given zero Fondon line, this optical line at 303 nanometers. They adopt the germanium as a component of the growth mixture, and these lines of germanium and silicon, they are shifting with the temperature, can be used as a thermometer. Here's the example. It's again collaboration with Weil group. Is a cell having now silicon vacancy doped nanodiamonds. We can track them, as I mentioned before, or during long time. So it's about 1 hour measurements. We see how the nanodiamonds is diffusing, and at the same time we can track the optical emission line. So it's tiny changes, but nevertheless they allow to track the temperature inside of cells during these measurements with about 1 Kelvin precision. Here summarizing this part, so I show you that these NV centers and silicon vacancy centers can have several sensing modalities. We spend most of the time with sensing magnetic fields, and just to give you a feeling how sensitive they are. So nowadays they can measure proton spin, a single proton spin, if they are 2 nanometers apart within 1 second measurement time. It translates to a sensing of the electron spin at 30 nanometer distance for 1 second measurement time. The NV centers are also sensitive to electric fields. Here we have not discussed this at all, but I just give you an example here of ODMR line with applied electric field. And this sensitivity translates an ability to sense 1 electron charge at 200 nanometer distance in vacuum. So of course, if you have water around, so this electric field will be shielded. But if you don't have a shielding effect, then you can measure 1 electron charge at 200 nanometer distance because of this 1 hour R square distance dependent of the field. So you are actually more sensitive to electron charge within V center than to electron spins. You can also measure forces. This is based on strain. So making diamond pillars and making them flexible if they are very, very thin. They can be used for measuring forces because bending of this pillar lead to strain similar to electric field effects on a V center, and that's can be translated to measurement of forces with the atto-Newton sensitivity. In some cases, quite compatible actually with other techniques like optical tweezers or or IFM as a force measurement device. And as we have discussed for temperature measurements, so the best sensitivity achieved is in the millikelvin range. It's a reasonable sensitivity. It's, of course, you can have microscopic thermometers that are much more sensitive, but not in combination with this nanoscale spatial resolution. So they when combined with spatial resolution, only fluorescent molecules can compete, but those are often affected by other effects like pH, and so they can be sometimes given not very clear results. All right, so now in the very last part, I promised to talk about hyperpolarization and use of NV centers not just to detect some biomolecule, but to enhance the imaging in context of MRI, transferring the polarization of the optically pumped NV center electron spin to nuclear spin. Why it is important? So MRI, which is based on NMR, is a golden standard in medical imaging. But as we have discussed it, usually it relies on a thermal polarization of nuclear spin, and sensitivity is very modest. So increasing sensitivity in MRI is usually about increasing the B field, and modern MRI scanners are already operating at 7 Tesla field, but there are some limits they can go, and of course it will never go above the limit given by critical current of superconducting coils. So there is not so much to improve in terms of improving magnetic field. And the experiments or the avenue that I would like to discuss today is to use optical polarization of electron spin to transfer it to polarization of nuclear spin, and then use a nuclear spin as a target for MRI imaging. One of the scenarios would be to take nanodiamonds that are functionalized to target certain molecule in a biological tissue. These nanodiamonds should have NV centers in them. One irradiates them with light, so then electrons of NV centers that get polarized, we can transfer polarization to carbon-13 nuclear spin in nanodiamonds, and then inject these nanodiamonds inside of body and image then in MRI scanner. In this case, nanodiamonds will be used as a tracers in MRI. One can also think about use of small size of nanodiamonds to allow polarization to diffuse out of the particles and polarize external to nanodiamonds nuclear spin. In this case, you can polarize metabolically essential molecules. And this is another very important application. So in both cases, you like to have very small nanodiamonds having NV centers and transfer polarization from the NV centers and nanodiamonds to the nuclear spins. So we have tested these protocols first in a large piece of diamond. Here you see a diamond with NV centers. It's not a nanodiamond, and irradiated this with light. And we have created a protocol that, or we applied the protocol that allowed the transfer polarization between electron spin and nuclear spin. This was done by matching the kind of the driving frequency of NV center electron spin to nuclear spin Larmor frequency, and this matching is called the Hartmann-Hahn condition. So if you do this, then electron spin loses polarization, and NV center get depolarized. Nuclear spins inside of this diamond getting polarized, all oriented. But NV center can be reused. You can shine again the light on it, it gets repolarized, and with this you can reach very high degree of polarization of this diamond. You can even image this diamond inside of MRI scanner, provided that even though the number of carbon-13 nuclear spin here is not very large. So this piece of diamond here is seen as a carbon-13 signal, and this is MRI image obtained in collaboration with Volker Rasche from Ulm University Medical Center. So in terms of benchmark and as imaging technique, this will potentially improve the sensitivity of MRI by orders of magnitude. You can think about medical imaging capacity of technique in terms of combination of sensitivity in molar and spatial resolution. Usually ultrasound, MRI, or computer tomography, they have a decent spatial resolution, but they cannot image tiny concentration of, or don't have a chemical specificity. So they fail in terms of molecular sensitivity. So for diagnostics or treatment assessment, you typically need sensitivities in imaging on the order of micromolar or better, and typically it's positron emission tomography, which is a key player here as an imaging technique. And so bringing the MRI sensitivity by 3 orders of magnitude, like an imaging particle of diamond targeting some biological molecule, will allow you to have to bridge this gap between low sensitivity of MRI and applicability in medical imaging. So here it's a few examples how one can do it, or some steps towards doing this. It's again important to have the nanodiamonds that are doped with a suitable concentration of NV centers. Yes, we see the tubes filled with micro nanodiamonds containing P1 center, and this is an NV center, and this is different sizes, micro and nano fractions. Experiments with polarization of nanodiamonds are not so trivial, because in the tubes they have all possible orientations. So this kind of nice driving of NV centers with some frequencies is challenging here, because the frequency of nanodiamonds, so this is the PR spectrum, are spread over several gigahertz of frequency range. So we have to find new protocols allowing to do this polarization transfer for very disordered in terms of orientation system. We can also dope these nanodiamonds with high concentration of NV centers by choosing a suitable irradiation dose. Actually, we can reach up to a few ppm even for 25 nanometers nanodiamonds. And so addressing this anisotropy in terms of orientation and spectral distribution can be done by beta polarization sequences. One of them is so-called pulse pol, and I think Nir was already shortly introduced in this. This is a sequence that allow you to make less sensitive protocols still polarize nuclear spin, but be less sensitive to detuning of polarization. It's similar to echoes that we have discussed before, but now this echo is designed to create a Hamiltonian, which is a flip-flop between electron and nuclear spins. And here you see the comparison of performance of pulsed protocol and this Hartmann-Hunt protocol, the efficiency of polarization transfer versus the tuning of microwave. For Hartmann-Hunt protocol, this efficiency drops very quickly with a small detuning, and for pulsed polarization transfer, you can tolerate the tunings of your NV centers on the order of 10 to 50 megahertz. And so this is a joint effort with Martin Plenier team at Ulm, who did the design of this pulsed polarization sequences. Now this can be applied now to these powders with all these elements. We have a pulse pole sequence for polarization transfer. We can apply it to powder spectrum, catching this about 10% of population of NV centers in this part of the spectrum. Actually, we also rotated the sample and the magnet to shuttle different nanodiamonds around, and with this we can improve the polarization of the carbon-13 or increase hyperpolarized diamonds by about 3 orders of magnitude for 2 micrometer particles, and by about 1 order, or like close to 3 orders of magnitude, 940 times over thermal polarization for about 100 nanometer particles. These particles, after having polarization of carbon-13 in them, can have a relatively long coherence time or relaxation time of these carbon spins. Here I show you how this nuclear spin relax after being polarized, and the time scale here you see it actually has 2 components. We think it's attributed to big and small particles. For larger particles, we have a relaxation time of nuclear spin about 1.8 thousand seconds, so you have half of hour your polarization leaves. And for smaller particles, we believe it's this short component. It's about a couple of minutes, but this is the time this nuclear spin polarization remains. This is the time, if you think about application of these nanodiamonds as a target for imaging, this is the time you have before you do your medical image. And the second application of this approach is to use this nanodiamonds and carbon-13 as a source of polarization for external nuclear spin. For this, you even can think about generating a core shell system and normal nanodiamonds having an NV center, and then the carbon-13 enriched shell, where the polarization can diffuse out and reach external liquids, which can be metabolic molecules, which can be then imaged in MRI. So this is a second approach where you have your basically NV center as a source of polarization for outside molecules to improve the polarization of arbitrary liquid outside and make it more universal, this approach. And so first steps towards this core shell synthesis have been demonstrated by Valery Davidov from Institute for High Pressure Physics of Russian Academy of Science in Paris. So here you see the core, very small particles that have been placed in a HPHC chamber and overgrown with carbon-13. You can see this core shell nature by measuring Raman spectrum. This Raman spectrum has 2 components. The 1332 wave numbers is 1% normal diamonds, and the smaller frequency Raman correspond to 100% enriched carbon-13. This is a shell. We can also show that this core and shells are really exist in a separation, because core was doped with NV center, and this NV center still have a normal DMR line not corresponding to carbon-13. So the core represented by this round transfer polarization to external nuclear spin. All right, I think I can skip a few last slides about bulk magnetometers and summarize again. So we have discussed it today. a few applications of NV centers. A lot of discussion about NMR. So you can detect molecules, spins in liquid with very high sensitivity in terms of number of spins, but so spatial resolution is not all. Also spectral resolution need to be improved, and so this is now ongoing work. Not so much was done using entangled spins, and I had one example how error correction can be used for improving the sensitivity, and I think that's very, very interesting to see how small-scale quantum registers can be used to improve the sensitivity of these measurements. And then we have discussed the NV centers endowment as a source of polarization for medical MRI imaging. Haven't talked too much about integrated magnetometers, but this is something that we can skip today.